Right. So I think this is the thing. Progress is gradual and slow. In other words, if you jump to some random place in the Ruliad, you pick a random program, you look at it, you know, when you first look at it, it's like, I don't know why I care about this. It's something where we have to have a kind of a, I don't know whether you can call it cognitive or intellectual history kind of path that gets there. We don't get to talk about until we've built sort of the ambient ideas, until we've built this kind of intellectual path, it doesn't really work to just jump to that place. It's like I could make up a word, and I don't know, I could make up a word for, I don't know, let's say look at clouds in the sky, and they have all kinds of weird different shapes. And we have a few names for a few of those shapes. Right now, we don't have a reason to care about the particular details of those shapes, but I can make up a word for one of those things. But until I can sort of tell you why we care about that, it becomes something that's very hard to. It's something we're sort of not connected to. I kind of think it's one of these things where it is there's sort of a sense of gradual progress, but you kind of can't, you can't kind of jump ahead. It's kind of like the computational irreducibility story, actually, that you can't kind of jump to a random place and expect to have understanding there. Okay, so this question of so this thing that's going on inside that's very complicated, that's computationally irreducible, what can we say about it? And we can still have something where there's complicated computations going on, they achieve goals we're interested in, we're happy, we're done. We can then go in, as you point out, and ask what's the science of what's happening inside. In a sense, the neuroscience has been that story of we know what we humans do. How does we know something about how the microscopic brain, works and neuron firings and so on. We don't have an intermediate language of neuroscience that is kind of the thing that is above the level of individual neuron firings and below the level of psychology, basically. And I think that's the question of can you find that and when can you find that is a very interesting question. I think one of the things that is a science point that when you have computational irreducibility, one of the necessary consequences of computational irreducibility is within a computationally irreducible system, there will always be an infinite number of specific little pieces of computational reusability that you can find. In other words, even though you can't say everything, there are lots of little pieces, little things you can say. In a sense, that's why, if we take it at a more general level, if you say, well, what inventions can we make? Given the physical world, which has computational irreducibility, what things can we predict? What things can we invent which have foreseeable behavior, and so on? And the answer is there will be an infinite collection of these things. We'll never run out of inventions, little pieces of computational reducibility that we can find in this ultimately computational irreducible universe in which we live. So in a sense, we're always finding these little jumps, the little pieces of computational reducibility. And those pieces of computational reducibility may be big enough that we can kind of live in them. The fact that we believe space is continuous, that is a feature of a slice of computational reducibility from the underlying computational irreducibility of this complicated, the way we set it up with this, rewriting rules for some hypergraph that's going on underneath. That's a very complicated thing. If we were stuck experiencing the world in terms of this hypergraph being rewritten all the time, we wouldn't be able to sort of go and lead our lives in a simple way. It's like, when you have molecules in a gas bouncing around, if we had to follow every molecule, that would be a very different thing from our typical experience of a gas, which is just this sort of continuous fluid. So I think the thing that in we're kind of we experience, it's very important to find these sort of slices of computational reducibility, because they're the things that we can build engineering, we can make a predictable life out of, and so on. And those are things which, again, but many of those, many of those pieces of computational reducibility we haven't yet found, we don't yet have names for. As we find them, we may be able to make use of them. And we may be able to kind of expand our experience of the world in a way which makes use of those things. For example, one question you can ask is, will there be a science of machine learning? That would be a reasonable kind of question. Is it going to be the case? Right now people say, well, and what might a science of machine learning look like? Here's an example. So typically in machine learning, you do a training, you're finding a particular path where you get to a good point where you have a nice trained neural net. Imagine you followed all possible paths. It'd be a computationally absurd, thing to do, but the universe does something very much like that in the way that quantum mechanics works in physics. One of the things that's taken me a while to get used to is the idea that the universe is a profligate waster of computational resources. It's constantly following all these different paths of history, which we conflate together when we actually experience the world, but it followed all these different paths. So imagine that you did that for machine learning. Not necessarily practical at first, but imagine that you could do that. And imagine you could start thinking about kind of that space of possible paths that were followed. Imagine you could start using ideas from physics to think about that set of possible paths. Imagine you could think about things like, you could think about sort of the formation of something like continuum space out of all of those different possible paths that might be followed. There are ways that you could imagine doing some kind of science where you start saying, well, there's an event horizon that will form in this part of sort of training space, things like this. Now, right now, that might be something where we would say, oh, that's really quite interesting science. It's irrelevant to the practicalities of machine learning. Or it might turn out that understanding things at that level with that kind of sort of generalization and then going back to the specifics might turn out to be really valuable. I don't know yet. I think that what we can say from our experience in understanding physics and fundamental physics is there are some very powerful techniques that one can use that in a sense have already been discovered in physics, that once we know that physics is computational, they can be applied. Those things that have been discovered in physics can be transported to lots of other areas, like, for example, machine learning. But in terms of, do I expect that there will be many well, another thing to say about architectures of neural nets and so on is, the principle of computational equivalence kind of tells you in the end it doesn't really matter. In the end, if you kind of bash it hard enough, it's going to be able to sort of learn, quotes, learn anything. Now, there may be, when I say bash it hard enough, there might be a factor of 1 billion difference in practice. And that makes big difference in the world as it is. But I think and the other question is, the thing that we've been sort of lucky about is that, as I was mentioning before, the neural nets that we have, when they generalize in fairly human ways. And I think we don't fully understand that. I think that's a fact about neuroscience as much as it's a fact about machine learning. I don't think that's something, you can't prove that. It's not something where you can get a mathematical proof this thing is going to generalize in a human way, because it depends how we humans work. And that's something that is really a matter of natural science, of neuroscience and so on to determine. But, there happens to be an alignment there, possibly because the underlying sort of McCulloch-Pitts level architecture is quite similar.